Okay. Gonna wait for 3 more, gonna wait for everybody, because today is the most important lecture of the year, hands down. This is the one skill that, I mean, you'll take a lot of stuff from this class and use it in future classes, but this is the main one. This is the one that you will see every year, and you will definitely know it, you know? Like, it'll hit hard, and then a bunch of your classmates will be confused because they got lazy in this section. And so you want to be so good at this, not only can you ace it, but you are good enough to assist your homies who cannot. Still waiting for 3 more. Hopefully everybody's here. Usually everybody is here. I don't have that many absent from my freshman group. But for today's lecture to be real good, for you to get the absolute most out of it, you want your calculators ready. So whatever calculator you have, bust it out and make sure that you have access to it for this entire lecture, because we're going to be using it for a bunch of different stuff. And then item number 2, I want you to try and describe what precisely is a mathematical function. Today we're going to talk about functions in general in our warm-up, because today we're going to be learning 3 brand new functions. All of the functions that you know would fit on a very short list. I think right now you guys know basically 6 fundamental functions. And you should know that out there in the world, there's basically an infinite number of functions, but you only know 6 of them. And the 6 functions that you know, they all have something in common. They all behave the same. So item 1, get your calculators ready. Item number 2, what is a mathematical function? Describe it in your own words, like don't just look it up. Yeah, don't just look it up. And to start this off, like I said, this is the most important lecture of the year. So if you're feeling tired, if you're feeling a little sleepy, get a little bit of exercise before we begin. Do a few jumping jacks, do some push-ups, do whatever it is that you do to stay fit, because exercise helps studying. It's like scientifically proven, which is why if I'm ever cramming for a thing, I usually structure my study time so that I do 45 minutes of studying, take an exercise break, shower, eat, and then come back to studying. If you need to study for 90 minutes, putting a break for exercise and food and rehydration in the middle is a big deal. So yeah, please, if you are feeling tired, do some exercise. I myself, I'm going to step aside here real quick. I'm going to do some squats because I also want to be at the top of my game today for this, because like I said, it's the most important lecture for y'all to pay attention to today. That also means it's therefore the most important lecture for me to teach. How's it going?
Good, pretty good.
Oh, that was a trick. If you're talking on your microphone, I know you're not exercising. Get away from the space bar, go exercise. Bamboozled. All righty. Okay. So, item number 1, calculator's ready. I myself am using a TI 84 Plus, and I'm going to be using this today basically to demonstrate the values of the decimals that we'll be taking. Your calculator will be different, but it's basically the same. The big deal is you need that sine, that cosine, and that tangent button. Item number 2, I'll give you all a few minutes to exercise, and then we'll come back to this major idea. What is a function? What is a function? Anybody?
Mr. Robinson, I have a question.
Okay.
On my calculator, like it has the sign, but with a -1 next to it. Is that okay?
That's the inverse.
You need both of those, and we'll be talking about that today.
Oh, okay. Yeah, I have both.
Oh, every calculator that has sine, cosine, tangent also has sine -1, cosine -1, tangent -1, which we'll be talking about today. But first thing, what is a mathematical function, or can somebody give me an example of a mathematical function?
I mean, I'd say like a mathematical function is in a sense an input that you add values to, and when you use that input, you will get another value from it. For a sense, if you add values into like a sine input on your calculator, you're going to get an answer from it.
So I'm not talking about anything yet, just pure concept. What is a mathematical function? And that basically captures it. But a mathematical function is a mathematical object. Mathematical object which takes an input. And since y'all are at this level of mathematics, the input variables are almost always x for whatever reason. And then it returns an output. And what do y'all normally call your output values?
Y.
Y.
Normally it's y. So basic, for example, if I had that y is equal to x squared, in this case, my function is the function x squared, I could come up with a table of values, x and y, and that is to say, I input 0, I output 0. I input 1, I output 1. I input 2, I output 4. I input 3, I output 9. And if you were to do this on and on and on and on forever, you would get all of the points that you need to graph this parabola. It is a function. It has inputs and it has outputs. Now, I think the other important thing to realize is that functions have inverses. There's a way to undo this. And to do that, we would solve for x. So how would I get x alone? What's the opposite of squaring something?
Square root.
Square root. So that is to say our inverse does the opposite. Our inverse would be x is equal to the square root of y. And what this would do is it would take all of our outputs and let us take them all the way back to inputs. Square root of 9 is 3, square root of 4 is 2, square root of 1 is 1, square root of 0 is 0. So here is the definition that we have to have in our head of a mathematical function. A mathematical function is an object which takes an input, returns an output, and functions have inverses. The job of an inverse is that it goes from the output backwards to the input. Are there any questions up through here? Is this okay?
Yeah.
Yeah, okay. So like I said, today's the most important lesson of the year, so let's just get straight into it. Today we're talking about section 4. Wait, what chapter is this? 8 or 9?
8.
8.4. Trigonometry. And so, trigonometry, defined, or as you'll often find it just called trig. Trig is the use of the Pythagorean theorem in conjunction with trigonometric functions in order to calculate unknown sides and angles. Trigonometry. What this whole skill is it's using the Pythagorean theorem alongside trigonometric functions, which are going to be the new functions we learn about today, in order to calculate the unknown side lengths and angle measurements of right triangles. Now today we're only going to limit ourselves to right triangles, but we are going to find that before the end of this chapter, this skill can actually be used to calculate the sides and angles of all triangles, and in fact all polygons, period, point blank. Is this okay?
Yep.
Yeah.
So we have that first part. We know that this is going to use the Pythagorean theorem. That is to say, for some given triangle, and yeah, for any given triangle, a squared plus b squared is equal to c squared. We know that to be true. That is a mathematical fact. However, let's now go ahead and define trigonometric functions. And their inverses. I'm going to now unmute everybody's microphone, which if you didn't know, that's a magical power that I have, so fair warning, all microphones being unmuted, because I know nobody out there is watching TV. Nobody out there is watching TV or playing video games, so when I hit unmute all, it's not going to cause any problems. Unmute all. Amazing. Okay,
Yay.
everybody is now unmuted. And so here is why I need everybody unmuted, because this is a thing that we typically do when it comes to trigonometry. I need to make sure that we all know the magic spell. And here is the magic spell.
Magic spell.
So,
Skedaddle, skedaddle.
Ka,
So
Ka, Toa.
SOHCAH TOA.
SOHCAH. So on the count of 3, we're all going to say SOHCAH together, and it's going to cast a magical spell that unwinds triangles. 1, 2, 3.
SOHCAH TOA.
SOHCAH TOA.
SOHCAH TOA.
SOHCAH TOA.
SOHCAH TOA.
SOHCAH TOA.
SOHCAH TOA. SOHCAH TOA.
SOHCAH TOA. SOHCAH TOA.
Chaotic.
Okay, magic. Everybody's muted again. Now, the reason why this is crucial is that if you forget nothing else, SOHCAH TOA is the thing that you remember that will allow you to solve all of the side lengths moving into the future. And here's how this works. A trigonometric function, a trig function, takes an angle and returns a ratio. The input of a trig function is an angle, and its output is a ratio. And we have 3 different trigonometric functions that were come up with by the ancient Greeks. Trigonometric function 1 is sine. Trigonometric function 2 is cosine. And trigonometric function 3 is tangent. On your calculator, this is always shortened to 3 letters, SIN, COS, and TAN. So should you need to use these on your calculator, we're only actually looking at the first 3 letters. But don't say sin, cos, tan. Everybody will know that you have no idea what you are talking about. No matter what, when you talk about these math objects out loud, you say the full name. You say sine, cosine, tangent. And so I'm going to start off by drawing a triangle, and I'm going to label exactly one of the angles inside of it. So here is a right triangle. Right triangle, right? That's my 90-degree angle. And I'm going to label one angle here, theta, Greek letter theta. And based on the position of this angle here, theta, I'm going to name these sides with letters. Now, I'm not doing the Pythagorean theorem, not right now, so I'm not going to use ABC. Instead, I'm going to use H, O, and A. First off, what is the deal with H? Why would I call this side H?
Because it's the hypotenuse.
H stands for hypotenuse. H stands for hypotenuse. And here's where these come from. This side is labeled with a capital O because it is on the opposite side of the triangle. Notice this angle is made of two side lengths, this length and this length. The length that does not construct the angle is known as the opposite, because it is on the opposite side of the triangle. This other side here, one of the angles that forms the, one of the sides that forms the angle, right, but is not the hypotenuse, we say that this is the adjacent side to the angle. This is the adjacent. And here's what SOH CAH TOA is talking about. SOH CAH TOA, SOH CAH TOA, SOH CAH TOA, SOH CAH TOA. This function, sine, if you do sine of theta, will return to you a ratio. Sine of theta is equal to, and I'm going to put parentheses here because theta is something we plug into sine, right? It's going to take the angle and it's going to do something with it behind the scenes inside of your calculator that is going to return a ratio. And the ratio that it is going to return is going to be the opposite side divided by the hypotenuse. That's what the SOH is in SOH CAH TOA. Sine is equal to opposite over hypotenuse. And this is just a set of letters and a sound that's easy to remember that helps us keep it straight. So this is opposite, then divided by hypotenuse. Similarly, cosine and tangent will also be defined out using SOH CAH TOA. So cosine of theta, take a wild guess. What is cosine of theta equal to?
Adjacent over hypotenuse.
Adjacent over hypotenuse.
Adjacent over hypotenuse. And finally, tangent of theta. Tangent of theta must be equal to what based on these letterings?
Opposite over adjacent.
Opposite over adjacent. And now some interesting stuff that I'll point out that you guys will run into later on in your life. These two ratios both have the hypotenuse in the denominator, and the hypotenuse is always the longest side. So one interesting feature of sine and cosine is the fact that literally no matter what angle you plug in, this ratio that it returns will always be less than 1 because the denominator has to be bigger than the numerator if the hypotenuse is the longest side of the triangle. It is also important to know that these trig functions have inverses. And we said in the warm-up, well, if a normal function takes an input and then it returns an output, what does the inverse do?
It's going to return the input.
It's going to give us back that input. So all of these guys have their own inverse functions. And just to warn you, there are two ways that you can see inverse functions written. Both of the things that I'm about to write are equivalent. Inverse sine, which would be sine to the -1, which is a button on your calculator, of something is exactly the same as arc sine. Depending on the book that you are using, the year in which it was written, the country that it's from, you might see this, which is really common in America, or if you're using a foreign textbook or if you study abroad, a lot of European countries use arc sine, but these are absolutely identical nomenclatures. I'm sorry, these are identical functions with different nomenclatures. But in this class, we'll be using this one here on the left because, you know, it's the USA.
What's a nomenclature?
Nomenclature is simply the way that we write down an idea for the sake of representation.
Oh.
It's like the difference between saying 2 times -3 or -3 times 2.
Oh,
You can represent multiplication with parentheses, or you can represent multiplication with a little x. These have the same content, but they have slightly different nomenclature.
yeah, okay.
Okay, so here's what I'm saying about these inverse functions. A regular old trig function takes an angle and it spits back to us a ratio. An inverse function takes a ratio and it spits back to us an angle. So this is to say that inverse sine of opposite divided by hypotenuse, if we were to plug that ratio into the function inverse sine, this will give us back theta. The same is true for cosine. inverse cosine of its ratio, the adjacent side divided by the hypotenuse. This will give us back that exact same angle. And tangent of adjacent divided by hypotenuse. This will also give us back that angle theta. So we have a new way that we can write down ratios of a triangle, and this technique up here will let us solve for side lengths. And down here, we have a technique that will let us take the side lengths of a triangle and let us solve for their angles.
Why doesn't the tangent have a -1?
Oh, also, I also made a mistake in it. So this is adjacent over hypotenuse. This is opposite over adjacent. I was on autopilot and I wrote the same ratio twice. I apologize deeply. Let me fix everything wrong I just did. So yeah, it's inverse tangent and it's opposite over adjacent. SOH CAH TOA works both ways, yeah? SOH CAH TOA. The function is inherently tied to the ratio, function tied to ratio, function tied to ratio. Great. Are there any questions on the notes up to here? So there should be no questions about doing math. We haven't done any math yet. This is all definitions. Okay.
What does the -1 mean again? Like
It
above
means
this
inverse.
inverse? Okay.
Yeah. So the way that this is read is inverse sine is sine to the -1. And you can also call it arc sine of that thing. It's the same idea. It's just North America, Europe region.
Okay.
Okay. And before we move along, before we talk about how to use your calculator in order to answer these questions, I got to hit y'all with a major warning. Big warning. There are two different ways to measure angles. And unit conversions can be confusing and tricky. And unit conversions have cost us to lose entire satellites simply because one team was working on the satellite in inches, another team was working on the satellite in centimeters. Somebody made a unit conversion wrong, and the satellite blew up. The same, huh?
Really?
Yeah, yep. Back when NASA still used inches and we were working with the European Space Administration. And ever since then, that's why NASA has also switched over permanently to the metric system.
Okay.
The same way that a marathon can be thought of as being 24 miles or 42 kilometers, those distances are exactly the same, right? You got 24 miles, you got 42 kilometers. It's the same length, but with different numbers. There are two different unit systems by which angles are measured. And if your calculator is using the wrong angle system, you're going to have a bad time. So what does an angle measure? What is the angle measurement based on?
How spread out the two side lengths are kind of touching each other in a sense. It's like
so we use angle measurements in degrees to measure the total separation between two rays. But what that unit is actually based off of is the circle. And here are the two different unit systems. There's the one that you are used to, which is degrees. And it's based off of a circle in the following sense, that if I had a circle, how many degrees make up a complete circle?
360.
So we go from 0 degrees, whoop, to 360 degrees, and this is the baseline definition. So if you want any of the angles here, we divide. So if I want half of a circle, that's 180. If I want a quarter of a circle, that's going to be 360 over 4, that's 90. If I want 3/4 of a circle, that'll be 270, and blah, 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 right? If you want to know how much is 10 degrees, you take the space between 0 and 90, you fold it into even ninths, and that little cut will be 10 degrees. So this is the definition of degree measure. There is another superior system by which we can measure an angle, and this is the method that scientists and engineers actually use, but for whatever reason, we don't teach it to you guys until your senior year of high school. The other way that you can measure the other way that you can measure the size of an angle is in a completely different unit system called radians. And the weirdest thing about radians, and I mean this is true of all units, we're taking an object and we're making a definition and sticking with it. Here's what makes the radian system different. Instead of it being 360 units, one circle in radians is measured out in 2 pi. So instead of this, right, so when I say 360, I'm saying, hey, I'm going to go all the way around a circle, that's 360. In the radian system, when we go all the way around a circle, we're saying we're going to go from here to here, and that is 2 pi radians. So this works exactly the same. If you want any sub-measurement, we're just going to, well, divide. I want half of a circle, well, that's 2 pi divided by 2, that's pi. If I want to know, well, what's halfway between 0 and pi, well, that's pi over 2. If I want to know what's 3/4 of this, well, that's 1.5 pi or 3 pi over 2. And if you wanted any other angle in here, again, all you do is divide. So same thing here, I got 90 degrees. If I divide that by 3, what's 90 over 3?
30.
30. That's 30 degrees. What's pi over 2 divided by 3? That would be the same as pi over 2 times 1/3. What's the rule about multiplying fractions?
They just multiply the numerators with the numerators and denominators with the denominators. So it'd be pi over 6.
Pi times 1 divided by 3 times 2. So this right here in radians is pi over 6. And here's the takeaway. 30 degrees is equal to pi over 6 radians. You could do this unit conversion for any one of these angle measurements. Now, full disclosure, you are not responsible for radians in this class. When you guys get to Algebra 2 or to pre-calculus, you will have literally an entire chapter about this stuff and why we would bother doing trigonometry and radians. However, I'm here to warn you that if your calculator is in the wrong mode, your calculator is going to give you the wrong answers in terms of trigonometry. So what y'all need to do for all of your different calculators, because my calculator may be different than yours, you have to Google the following phrase, change, and then type in the name of your calculator, whatever your model is, radians to degrees, and you need to look up how to do that on your own calculator, because if it's in the wrong mode, if it's in radians instead of being in degrees, your calculator is going to betray you and it's going to give you the wrong answers. In this class, you always want your calculator to be in degree mode because all of the questions that we are going to work on are going to be in degree mode.
But even if it's already in degree mode, we should still do it, like it won't make a difference.
Leave it in degree mode if it's already in degree mode. So if you're looking at your calculator screen and at the bottom of the readout, it says deg, you're good. Just don't touch it. But still, I would look this up anyway for your calculator, just in case it ever gets changed out of that mode if the battery dies and it resets to radians so that you could change it back.
Wait, so you need it in deg and not radians?
You want it in deg, not rad.
Okay.
And how you switch it will be different for every calculator. So when in doubt, Google it, change whatever the make and model of your calculator is. In my case, it's the TI-84 Plus. And if you look up how to change radians to degrees, you'll find a tutorial.
So it already says deg, that means you're fine?
Yes. And we're about to do a test case that will allow us to figure out whether or not we're doing it right. And so here's what we're going to do. We are going to now draw a very familiar triangle, a Pythagorean triple who we have dealt with before. And we are going to start off with the following information. Here's all that we know. This is 5, and this is 13. And on the inside here, I'm going to label two of these angles. This here is an angle theta. This here is an angle phi. And here's what I want to do. This question is going to have 8 parts to it. I want tangent theta. Oh, you know what? I'll be nice. I'll lay it out the same order as we had it before. I want sine theta. I want cosine theta. And I want tangent theta. I want sine phi. I want cosine phi. And I want tangent phi. Now, one interesting thing, and this is unrelated to the question, though we will come back to it later. What do theta and phi add up to?
90.
They have to add up to 90 because all of the angles in a triangle add up to 180. This is 90, so these other two have to add up, so that 90 plus 90 gives us 180. So we know that those two angles in here that we're playing with, they are acute. This is a Pythagorean triple we've seen before, so by the Pythagorean theorem, what's this other side?
12.
12. This is the 5, 12, 13. So we know that that other side there is 12. If you don't believe me, hit it with the Pythagorean theorem. And so for this first part, we're just going to write out all 6 of these ratios for this triangle. So, SOH CAH TOA. Sine is equal to what?
Opposite over hypotenuse.
Opposite over hypotenuse. So from here, the opposite side is 5, and the hypotenuse is 13. Sine theta is 5 divided by 13. Up next, cosine theta. Adjacent over hypotenuse, 12 over 13. Tangent theta. What ratio is that according to SOH CAH TOA?
Over adjacent.
Opposite over adjacent. 5 over
12.
All 3 of these are correct trigonometric ratios.
Wait, we don't even have to divide them. The answer is just 5 over 13.
What do you mean divide them?
Or like, do we just leave it 5 over 13? We don't do anything.
What could you do with it?
Simplify it? I don't know.
13 is a prime number, nothing simplifies? Right?
Okay.
Okay.
But if we
Isn't it 5 over 12?
Opposite over hypotenuse, opposite over hypotenuse.
If we could simplify it, should we simplify it?
You can, and it wouldn't change the answer. So if this was 5 over 10, you could turn it into 1 over 2, and you would get all the same answers.
Oh.
That's a great question. Now up, down below. Sine of phi. What is that? Why would I write a second row of these?
Because you're solving for something else.
Yeah, so how will the answer be different? What are we going to get instead?
Oh, the opposite angle would be
the inverse.
Yeah, it would be 12. It wouldn't be 5 anymore.
Very good.
Yeah.
Please notice that if now, instead of talking about this angle, we're talking about that angle. Sine of this angle is still going to be opposite over hypotenuse, but if we're moving from this perspective to this perspective, that changes what the opposite side is. So for phi, the opposite side is 12. The hypotenuse is still the hypotenuse, so sine phi here is actually 12 over 13. And cosine phi will also be different. For this guy, what's the adjacent side?
5.
5.
Cosine phi will be equal to 5 over 13. And then finally, tangent of phi is going to be opposite over adjacent. So what is that one?
12
over 5.
Hey, great. Those are all 6 of the trigonometric ratios that we can write for this triangle. You cannot write trigonometric ratios for the 90-degree angle. It only works for acute angles. And now here, we haven't actually solved anything. This is pure definitions. This is pure notation. But here is one really wild thing that we can do with these trigonometric ratios. I want to solve for theta.
But no matter which angle you look at it from, is the hypotenuse always the same?
Very good. That is an important takeaway. No matter what angle you look at this from, the hypotenuse is the same. It's always the longest side.
Yep.
So now what we need to do is we need to solve for theta and for phi, and we'll know that we did it right because in the end, they'll add up to 90, right? We better get two complementary angles if we solve for them independently. Now, here's an important first step. I want to solve for theta. Should I use sine, cosine, or tangent?
Sine?
We could use sine and it would give us the correct answer, but do we have to use it?
No.
We could
No,
use
every
them.
single thing.
It doesn't matter which one we use. You can use sine or cosine or tangent. Any one of these three will give you the exact same answer. And now, let's go ahead and do it. I'm going to say that I have sine of theta is equal to 5/13. And before we said that if we want an angle, we're not going to use sine. Instead, we're going to use inverse sine. And here's why that works. I'm going to take inverse sine of both sides of my equation. And what I'm about to write looks a lot like the following. Let's say that I have x squared is equal to 9. What is my function?
X squared.
And so what is the inverse of x squared? What's the opposite of squaring something?
Square root.
Square root.
Square root.
And algebra says that as long as I do something and I do it to both sides, I'll get the correct answer. So if I want to get rid of that squared, I take a square root on the left, and to keep it equal, I take a square root on the right.
Yeah.
On the left-hand side, our inverse functions cancel. The square and the square root go away, and I get x is equal to
3.
plus or minus 3.
Oh,
Yeah.
yeah.
So I have a function, and I want to get rid of it, so I hit it with its inverse function. I'm going to do the same here. I have a function called sine. What is the inverse of that?
Inverse sine.
Inverse sine. So I'm going to hit both sides of this equation with the inverse sine. So this is going to be inverse sine of sine theta. And this is going to be equal to inverse sine of 5/13. Now notice, the same way here, these two functions cancel out because they're inverses. Guess what happens on the left?
It cancels out.
That is the point. And this will give us that theta, that angle measurement, is equal to inverse sine of 5/13. And you'll notice that this is exactly the same as the definition from the previous page where I said that inverse sine of opposite divided by hypotenuse will give us back the angle. I think this is an easier way to memorize how and why that's true. Is this okay?
Yeah.
Okay.
Wait, we didn't get a number.
We're about to.
Oh, okay.
So on our calculators, I first need to make sure that mode is in degrees. And this is going to be different for all of your calculators, which is why I told you to Google it. So I certainly hope your calculator is in degrees, not radians. If you do it in radians, you'll get the wrong answer. And so what I'm going to do is, and this is going to be true of all of your calculators, you'll notice that you have sine, cosine, tangent in line. We don't want that. We want the inverse. And that's right up above in a different color. The way that you access that button is by using your two colored buttons on your calculator. For me, they're called second and alpha. So if I want the blue inverse sine, first I hit second, boop, then I hit sine, and when it pops up on my screen, it appears as sine to the -1, which is inverse sine. Now I'm going to feed it the ratio, 5 divided by 13.
22.
And we get that theta is equal to 22.62 degrees. For all for all questions in this section, please give me 2 decimals, no more, no less. So this is telling us that theta is equal to 22.62 degrees. That is definitely our answer. And you should notice that we just used side lengths to calculate an angle, which is something you have never done before. You can use side lengths to calculate angles. Just know that the route to doing this is sine and cosine and tangent.
I have a question. All the things that we've like learned about triangles, are those not trigonometry up till now?
No, what we're doing now is trigonometry, specifically the use of sine, cosine, and tangent.
Oh, so it's not like just learning about triangles.
No, it's not learning about triangles in general. The use of this particular skill, relating angles to sides and sides to angles, is trig.
Oh, okay.
Is there another question out there?
Yeah. So for writing the answer, can we do that like theta is approximately, or just we do equals?
That would be the most correctest way to write it.
Okay.
Yeah.
Wait.
But I won't make you do that.
Approximate.
Yeah, to say it's approximately equal to would be the most correct way because we rounded. And here's what I want y'all to notice. You could have used sine since we had all the side lengths. Cosine and tangent will give us the same answer. So second, cosine, but to make sure it comes out the same, we have to use the correct ratio for cosine. That's 12 over 13. Hey, it's exactly the same.
How?
And second, tangent, 5 divided by 12, it's also exactly the same because all three of these ratios are actually talking about the exact same triangle. Now,
which one it doesn't matter which one you use.
It doesn't matter. Whichever one is easiest, whichever one you have access to.
Okay.
Now, don't get me wrong. You're not going to learn what sine, cosine, and tangent are actually doing until pre-cal. That's a completely different discussion. I can show you that sine is actually a different formula that I can write out, and it's really long and difficult. But for the sake of this class, there are buttons on our calculators that give us the correct answer. Nothing more, nothing less. Let's go ahead and do the exact same thing here for phi. And I'm not going to use sine. We already did that. So do you want me to use cosine or tangent?
Tangent.
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 Okay.
Ms. Robinson, I got the answer.
Good. And so this was a quick aside to talk about functions and function math. So tan phi is equal to 12 over 5. Therefore, phi is equal to inverse tangent of 12 over 5. And that means that angle phi must be equal to, again, I'll feed this to the calculator, second tangent 12 divided by 5, 67.38 degrees. 67.38 degrees. And what do you notice about these two angle measurements?
They add up to 90, so therefore it's correct.
They add up to 90 degrees exactly. Theta plus phi is equal to 90 because your calculator knows that we are talking about a triangle, and your calculator knows the triangle internal angle theorem. It knows that they have to add up to 180 in total. So it knows that the acute ones have to be 90. This always works. Sine, cosine, tangent, absolute mind trip. Super crazy to think about the fact that this is even capable of working. So you'll notice that in most lectures where people talk about sine, cosine, tangent, first they teach you to solve for a side. I like to show you how to solve for an angle first because this is the hard one. Now we're going to do our second and final example for the day. We're going to use this stuff to solve for an unknown side length. Is that okay?
Yeah.
Yeah.
Okay. Major example, example 2. And this is right now, this is going to be the most common type of trig question that you might ever have to deal with should you go on to be a scientist or an engineer. This is the big calculation that you want to be able to do. Complete the triangle. And as I write this out, how many parameters does a triangle have? How many numbers do we affix to it?
6.
We affix to a triangle 6 values. 3 whats, 3 whats.
3 angles, 3 side lengths.
Wonderful. And here's what the major lesson of trig is. Because of the special way in which triangles behave, I only have to give you 3 of them. If I give you 3 numbers for this triangle, I'm actually giving you all 6 of them as long as you know how to do the math. So here's all that I'm going to tell you about this triangle. This angle measurement here, the small one, That's 23 degrees. So this right here is 23 degrees. And the length of the hypotenuse, oh, that's not a ruler. That's a ruler. The length of the hypotenuse is 7.3 centimeters. And so here's what I would like you to do. From this angle's perspective, we need to complete the triangle. And right now I've given you 3 numbers, right? What 3 numbers have I given you?
That it's 90
3, 23, and 90.
23, 7.3, and 90.
Good. The only reason why I ask is to keep in mind that this is a given number. This is 90. This is how we know that trig will even apply in the first place at all. But to complete the triangle, I'm also going to need this unknown angle here, angle phi. I'm also going to need over here side length A. Oh, I'm sorry, we should use lowercase letters for side lengths just because it's traditional. Side length A and side length B. So let's get the easy part out of the way. What is phi?
67.
We instantly know that phi is 67 degrees because the acute angles of our triangle, they have to be complementary. These guys have to add up to 90. So if this is 23, this is necessarily 67. But now for the new part. Let's go ahead and solve for side lengths A and B. How would you like to solve, or sorry, which one would you like to solve for?
A.
Okay, A. And so here's what we need to do. We need to use our brain and we have to realize, okay, I have this angle. What number were we given?
23.
That's the angle, but what side length were we given?
Oh, 7.3.
Which is the
Hypotenuse.
So we were given the hypotenuse. And if we're going to solve for A first, what side length is this with respect to 23?
Opposite.
Opposite.
That's the opposite. So I have the hypotenuse and I want the opposite. What ratio is that?
Sine, opposite over hypotenuse.
That is sine. And not only do we use SOH CAH TOA forward, so we use SOH to remember that sine is equal to opposite over hypotenuse, but we're also using it backwards. So in this case, we're saying that I want the opposite and I have the hypotenuse. Ding, 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 ding. Sine. So you want A? That's great. Sine of 23 degrees is going to be equal to opposite over hypotenuse. This is going to be equal to A divided by 7.3. How do I get A alone?
You're going to have to multiply both sides by 7.3.
7.3.
I'm now going to multiply both sides of this equation by 7.3 times 7.3. The point of this is so that on the right-hand side, 7.3 and 7.3 cancel out. And this is telling me that A is going to be equal to 7.3 multiplied by sine of 23 degrees. And I'm going to enter this into my calculator all in one go. So that's going to be 7.3 times sine of 23. We're not using inverse sine here. We're using regular old sine. So notice I didn't hit the second button. There is no sine to the -1, just regular old sine. Boop. And that's telling us that that opposite side length A, and again, round it to 2 decimals for this section, A should be equal to 2.85 centimeters. And, you know, why would I use a protractor to get this and a ruler to get that?
His ruler measures the length, but a protractor can give you the angle.
Oh, no, that's true in concept, but I'm saying, why do you think it is that I wouldn't just make up numbers and throw them down, but I would draw a triangle and then actually measure it for you?
Because
You know that
it could be any.
So we know that it can be applied in real life.
Yeah, I'm making the major bet here. I'm doing a little bit of science. This is our hypothetical answer for length A. This is what the math tells us. Let's see if it's right. Oh, what do you know?
It's right.
2.85 centimeters precisely. It's 2.8, and then it's halfway between 2.8 and 2.9. Oh, sorry, it's from my perspective. Let me fix it from the camera's perspective. Yo, you see that? You see that 2.85? That means your calculator knows about what is going on in my office. Your calculator allowed you to calculate a real length that you don't have access to. This is a real length. This is in my office on a piece of paper, and somehow your calculator knows about it.
That's
Yo,
crazy.
Trig is witchcraft. Okay, now let's also go ahead and solve for B. And the way I'm doing this is best practices. Technically, now that I have this and I have this, we could solve for B by using the Pythagorean theorem. Don't do that. Try not to reuse values that were rounded off. Because this was rounded off, I don't want to take it and plug it back in. We'll get a slightly crappier answer for B than the other technique I'm about to do. Consider the following. From this angle's perspective, what is the name of side length B?
Adjacent.
Adjacent.
And the side length that we were given to start is the hypotenuse. So CAH TOA.
Cosine. So let's use CAH because there's adjacent and hypotenuse.
Very good. Adjacent and hypotenuse is CAH. Cosine of 23 degrees is going to be equal to adjacent divided by hypotenuse, B divided by 7.3. So if I want B alone, I'm going to multiply both sides by 7.3. B is going to be equal to 7.3 cosine of 23 degrees. So again, I enter this, oh, the brightness changed. I'm going to enter this into my calculator now in one step. 7.3 times cosine 23. And this tells us that side length B is equal to 6.72 centimeters. And would you look at that, we just completed our triangle. We started off with 3 of the numbers for it, and we just got 3 of the numbers back. I gave you this angle, this angle, this length, and we were able to take those 3 digits and build out the other half of the triangle. Brah, brah, brah. Okay. Now, one other major check, and this is overkill, but you know we have about a minute left, so this is just right. What theorem should all of these side lengths obey?
Pythagorean.
Yeah. So a good way to check this stuff, if you have the time to do so on a trig test,
A squared, B squared equals C squared.
Plus B squared equals C squared.
Exactly. Just check them against the Pythagorean theorem. So if this is correct, if your calculator is somehow aware of this triangle's existence, then the side lengths that we just got should fulfill the Pythagorean theorem. And of course, it's not going to be exact because of slight rounding errors here and here. So as long as it's close, real close, we will accept this as having worked out. So on the left-hand side, I got 7.3 squared, 53.29. And if this is all valid, then I should get a really close number on the right-hand side. 2.85 squared plus 6.72 squared. Y'all ready?
Sure. Yeah.
53.28. Because of rounding errors, I'm going to go ahead and say that that is close enough. They are approximately equal to each other. And like I said, the big takeaway here is that somehow your calculator knows exactly what you were talking about when you talk about sine and cosine. And those values that you get match these values on my page. Oh, I forgot to measure B, huh? 6.72?
Probably exact.
6.7 and just over. So, sine, cosine, and tangent. They take an angle and they give back a ratio. That lets us solve for sides. Or if you use their inverses, those take a ratio and give you back an angle. But in either case, if you are given 3 of the numbers on a right triangle, you can use SOH CAH TOA in conjunction with the Pythagorean theorem to always get your other 3 digits, allowing you to always complete the values for an unknown right triangle. Today I'm going to assign your homework, and I believe that if you are hardworking and maybe a little talented at math, this is all of the notes that you need in order to do the entire homework assignment on your own. However, tomorrow we're going to have a chance to work on it together after I do a little bit more lecture, just because this is all the fundamentals, but I want to show you guys some weird ways in which this meshes with our previous sections. Tomorrow I want to show you the sine, cosine, and tangent values of 30, 60, and 45. That is to say, we're going to look at what this trig is like for our special right triangles. And then after that, we'll have the rest of the period tomorrow to work on the homework. And like I said, this is the most important section of the whole year, which means it's the most important homework of the whole year. Do a good job on it. Are there any questions on what we talked about today?
No.
Nope.
Not really.
Tight. So, like I said, most important lecture of the year. This skill will follow you for the rest of academia. I'll post the homework, and you all have a very nice day. I got a midterm this afternoon, and I'll see you tomorrow.
Thank you. Good luck.
Bye.
Thanks. I'll
Bye,
need
Mr.
it.
Robinson. Good
Yeah,
luck.
thank you. Yeah, I definitely need it.
Yeah.
I'm screwed. Bye, everybody.
Bye.